Machine learning can feel like magic, models that translate languages, generate images, drive cars, write code. But underneath all of it, there is no magic. There is mathematics, and surprisingly little of it. In this video, I want to give you the intuition behind that mathematics, not dry formulas to memorize, but a feeling for what each idea is actually doing. Because once you have the intuition, the equations stop being scary. They become obvious. Everything in modern machine learning is built on 4 areas of maths: linear algebra, that's the data, vectors and matrices, and the geometry of moving them around, calculus, that's the learning signal, slopes and gradients that tell the model how to get better, optimization, that's the training loop, rolling downhill on a landscape of error, and probability, that's how we handle uncertainty. We'll walk through all 4 in order, starting from the rawest numbers a model sees, and ending with a trained, calibrated model. But before any of that, I want to start with a simple, almost playful idea. The idea that one single problem can be solved in many different forms. Let's begin there. Here is the big idea for this first chapter. The same problem can be written in many different shapes, and choosing the right shape is what makes a hard problem easy. I'll show you 3 phases of this. First, a multiplication you can solve just by drawing lines and counting. Then a word problem about a restaurant that will turn into 2 lines crossing on a graph. And finally, that very same problem collapsed into a single compact equation, which turns out to be linear algebra. Let's start with the lines. This is sometimes called the Japanese multiplication trick, and it looks like sorcery the first time you see it. Watch. I want to multiply 21 by 13. Instead of doing it the way we learned in school, I'm going to draw it. For the first number, 21, I draw 2 lines, then a small gap, then 1 line, 2 and 1, 21. For the second number, 13, I draw lines crossing the other way, 1 line, a gap, then 3 lines, 1 and 3, 13. Now I just count where the lines cross. The crossings naturally fall into 3 diagonal columns. The left column is the hundreds, the middle column is the tens, and the right column is the units. Count the dots. 2 in the hundreds column, 7 in the tens, 3 in the units, 2, 7, 3, 273. And that is exactly 21 times 13. Now I'm not suggesting you do your taxes this way. The point is deeper than the trick. We took a multiplication, pure arithmetic, and turned it into a geometry problem about counting intersections. Same answer, completely different form. That single idea changed the form, and a hard problem becomes an easy one. Is the thread that runs through this entire video and through all of machine learning. Let's see it again with a real world problem. Real problems don't arrive as neat equations. They arrive as stories. So let's take a story. It's a busy night at a restaurant. A chef works for some number of hours. Let's call that X. An assistant works for some number of hours. Call that Y. We are told 2 facts. First, together the 2 of them worked 6 hours. Second, the assistant worked twice as many hours as the chef. The question is, how many hours did each one actually work? Now here's the first real skill in all of mathematics, turning each sentence into an equation. Watch what happens when I translate. The first fact, together they worked 6 hours, becomes X plus Y equals 6. The second fact, the assistant worked twice the chef's hours, becomes Y equals 2X. 2 sentences, 2 equations, 2 unknowns, 2 facts. That balance, as many equations as unknowns, is exactly what makes a problem solvable. And when we solve it, we get the chef worked 2 hours and the assistant worked 4 hours. Check it against the story. 2 plus 4 is 6, correct? And 4 is twice 2, correct? The words and the numbers agree. But solving it by hand is the boring part. The interesting question is, what does this problem look like? Because if we can see it, we can understand it. Let's draw it. This is the Cartesian plane, just a horizontal axis and a vertical axis, the coordinate system you've seen since school. And here is the beautiful fact. Every linear equation, when you draw it, is a straight line. Each of our equations is in the form y equals mx plus b, where m is the slope of the line, how steep it is, and b is where it crosses the vertical axis. Our first equation, x plus y equals 6, rearranges to y equals minus x plus 6. a line sloping gently downward. Watch it draw. Our second equation, y equals 2x, is a line through the origin climbing steeply upward. For every step right, it goes 2 steps up. Watch that one draw too. Now look at where the two lines cross. That single point at x equals 2, y equals 4 is the only place that sits on both lines at once. And a point on both lines satisfies both equations at once. So that crossing point isn't just a pretty picture, it is the answer. The chef worked 2 hours, the assistant 4. We didn't do any algebra. We let the geometry do it for us. And that is a profound shift. We just solved a problem not by manipulating symbols, but by moving into a space, the Cartesian plane, where the answer is simply the place two lines meet. We now know we can solve problems by choosing the right space to put them in. Hold on to that, because it's the whole reason linear algebra exists. But first, can we make this even more compact? Watch what happens when we stack our two equations on top of each other and pull out just the numbers. The coefficients, the numbers multiplying x and y, form a grid. We call that grid a matrix, and here we'll name it capital A. The two unknowns, x and y, stack into a little column we call a vector. And the answers on the right side stack into another vector, b, and now the entire system, both equations at once, collapses into three symbols, ax equals b, that is linear algebra in a nutshell. A matrix times a vector of unknowns equals a vector of answers. And here's why that's powerful. To solve it, we do one operation. X equals A inverse times B. The inverse of a matrix is like dividing. It undoes what A did. Watch, when I solve with the inverse, I get back X equals 2, Y equals 4. The same chef and assistant answer. But here is the part that matters. Solving two equations by hand, you could do on paper. The compact form, AX equals B solved by the inverse, doesn't care whether you have two equations or 10,000. It's the exact same operation at any size. That scalability, that one clean idea handling millions of unknowns at once, is precisely why machine learning is written in the language of matrices and vectors. So let's go learn that language properly from the very beginning. Linear algebra is the language of the data. Every single thing a model sees, a word, a pixel, a user, a sound, is turned into a list of numbers. And once it's numbers in a grid, we can rotate it, stretch it, compare it, and compress it. Roughly 99% of the compute inside a deep neural network is one operation, multiplying matrices. So this chapter is the foundation under everything. We'll start with the single most basic object, the vector. So what is a vector? Two answers, and they're the same answer. The first answer, a vector is just an ordered list of numbers. Here, this one has two numbers, an x component and a y component. Watch the bracket at the top change as I move the arrow. The second answer, a vector is an arrow pointing from the origin of the center out to a point in space. The two numbers are simply how far across and how far up you travel to reach the tip. As I drag this arrow, the red component is the horizontal distance, the green component is the vertical distance, and the length of the arrow itself is the size of the vector. Now, why does this matter for machine learning? Because in ML, everything is a vector. A word like king becomes a list of maybe 300 numbers. A photo becomes a list of thousands of numbers, one per pixel. A customer becomes a vector of their behaviors. Once your data is a vector, an arrow in space, you can measure how long it is, which direction it points, and how close it is to another arrow. And those measurements are the whole game. Here we only have two dimensions, because 2 is what I can draw. But nothing stops a vector from having 3 numbers or 300 or 1000. The maths is identical, we just can't picture a 1000-dimensional arrow. The intuition you build here in 2 dimensions carries all the way up. If a vector is an arrow, a matrix is a machine that moves arrows. A matrix transforms space itself. Here's how to read it. A matrix is a grid of numbers, and the trick is to read it by its columns. The first column tells you where the red basis arrow lands after the transformation. The second column tells you where the green basis arrow lands. And once you know where those two arrows go, the entire grid follows along. Every point in space gets carried with them. Watch as I turn these knobs. The whole plane rotates, stretches, and shears. That is a matrix, alive. Look at the shaded square. It starts as a unit square, and the transformation warps it. Its area has a special name, the determinant. The determinant tells you how much the matrix scales space, and watch what happens when I tune the knobs so the determinant goes to 0. The entire square collapses flat onto a single line. Space has been crushed into one dimension, and once that happens, the matrix is singular. It can't be undone, there's no inverse. Information was destroyed. Now connect this back. To transform a vector, you multiply it by a matrix, and out comes a new transformed vector. Chain several matrices together, and you get matrix multiplication, the single most common operation in all of deep learning. And here's the real-world hook. This is exactly how attention works inside a transformer, inside the large language models everyone is talking about. When a model processes a word, it multiplies that word's vector by learned matrices to produce its query, its key, and its value, the famous Q, K, and V. Each of those is just this, a vector transformed by a matrix into a new vector that means something different. Every time a language model pays attention, it is doing exactly what you're watching on this screen. Two of the simplest things we do with vectors are add them and subtract them, and both have a clean visual meaning. To add two vectors, you place them tip to tail, walk along the first arrow, then continue along the second. Where you end up is the sum, the purple arrow. It's the combined journey of the two. As I move either arrow, the purple sum follows. To subtract a minus b, you get the green arrow, and it points from b to a. Subtraction is the difference between two states, and that's not a trivial detail. In machine learning, the difference between where the model is and where it should be is exactly an error signal. Subtraction is how a model measures how wrong it currently is, and that error is what drives all the learning we'll see later. So this humble little green arrow is quietly the seed of training itself. If you remember one operation from this entire video, make it this one. The dot product. It is the single most used calculation in all of machine learning. And once you feel it, an enormous amount of ML suddenly makes sense. Here's the definition in words. The dot product of two vectors, a dot b, equals the length of a times the length of b times the cosine of the angle between them. Don't let that scare you. The cosine is doing all the intuition. Let me show you. Watch the number as I rotate b. When the two arrows point the same way, when they are aligned, the dot product is large and positive. Now I'll rotate b until it's at 90 degrees, perpendicular to a, and the dot product drops to exactly 0. Perpendicular vectors have 0 dot product, they share nothing. And if I keep going until b points the opposite way to a, the dot product goes negative. So the dot product is a similarity score. Positive means these point the same way, they agree. 0 means unrelated. Negative means they oppose each other. It takes two whole vectors and crushes them down into a single number that measures how aligned they are. Two reasons this is everywhere. First, that green bar is projected onto B. The shadow one vector casts on the other. And the dot product is the length of that shadow scaled by B. Second, and bigger, the dot product is the exact calculation every single neuron in a neural network performs. A neuron takes its inputs, multiplies each by a weight, and adds them up. That sum is a dot product between the input vector and the weight vector, billions of times per second. That's what a network is doing. And the real world payoff, this is how machines measure whether two words mean similar things. In word embeddings, the technology behind Word2Vec, every word is a vector, and the dot product between king and queen is high because they point in similar directions, while king and banana is low. And in the attention mechanism inside every large language model, the model decides which words to focus on by taking dot products between queries and keys. When ChatGPT figures out which earlier word a pronoun refers to, that is a dot product. This one little operation is the heartbeat of modern AI. Let's quickly organize the family of objects we've been meeting, because they all have names and the names describe their shape. A single number all on its own is a scalar. A list of numbers in a line is a vector, one dimension. A grid of numbers is a matrix, two dimensions. And the general version, with any number of dimensions you like, is called a tensor. That's the tensor in TensorFlow. Why do we need more than two dimensions? Watch. A single color image already needs three dimensions: height, width, and color channels, red, green, blue. And we almost never process one image at a time. We process a batch of them. That adds a fourth dimension. So a batch of color images is a 4-dimensional tensor. Batch, height, width, channels. And as I slide these knobs, you can see how fast the total number of values grows. Tensors are simply how we keep all that data organized so the hardware can crunch it efficiently. Same idea as a vector, just more axes. We keep talking about the length of a vector. But it turns out there's more than one way to measure length, and the choice has real consequences. The everyday one is the L2 norm, also called Euclidean distance. It's the straight line as the crow flies distance, the square root of x squared plus y squared, Pythagoras theorem. All the points the same L2 distance from the center form a circle. But there's another, the L1 norm, also called Manhattan distance. Picture walking in a city laid out in a grid, like Manhattan. You can't cut diagonally through buildings. You walk so far along one street, then turn and walk so far along the other. So L1 distance is simply the absolute value of x plus the absolute value of y, the total blocks walked, and all the points the same L1 distance from the center form a diamond, not a circle, because of those sharp corners. Those corners matter enormously. In machine learning, when we penalize a model using the L1 norm, those sharp corners push many weights to land at exactly 0, switching features off completely. That's how we get sparse, simple models that automatically select only the features that matter. L2 shrinks weights gently, L1 zeroes them out. Same word, length. Two different geometries, two different effects. The dot product gave us a number that's biggest when two vectors align. The cross product is its mirror image. It's biggest when they're perpendicular. Geometrically, the cross product measures the area of the parallelogram that two vectors stretch out. Watch the shaded region as I move the arrows. When the two vectors point in nearly the same direction, when they're almost parallel, the parallelogram is squashed flat and its area drops to 0. As I open them up toward 90 degrees, the area grows to its maximum. So while the dot product asks, how much do these agree? The cross product asks, how much do these differ? How independent are they? Zero area means the two vectors are redundant, lying along the same line. Large area means they genuinely span different directions. That idea, measuring how independent two directions are, is going to come straight back when we talk about the rank of a matrix and about principal components. It's the same question wearing different clothes. This is one of the most important and most beautiful ideas in all of linear algebra. So let's slow down and really see it. Eigenvectors. Remember, a matrix transforms space. It grabs every arrow and knocks it off in some new direction. Watch the spinning gray arrow, that's an input vector v, rotating through every possible direction. The blue arrow is what the matrix does to it, a times v, and you can see that for most directions blue points somewhere completely different from gray. The matrix has rotated it, but, and this is the magic, there are a few special directions where the matrix does not rotate the arrow at all. It only makes it longer or shorter along the very same line. Those special directions are the eigenvectors, shown here in green. An eigenvector is a direction that the matrix only stretches, never turns. And the amount it stretches by has a name, the eigenvalue, the Greek letter lambda. That gives us the single most famous equation in linear algebra, a times y equals lambda times phi. In words, when the matrix A acts on a special vector v, the result is just that same v, scaled by a number lambda. The arrow keeps its direction, only its length changes. Now watch this, I'm going to tune the matrix so that it's a pure rotation. See, the green eigendirection lines vanish. There are no real eigenvectors because a pure rotation knocks every direction off course. Nothing stays on its own line. That's a matrix with complex eigenvalues. It's all spin, no stretch, and now I'll bring it back. As the matrix becomes more stretch-like, the green eigenvectors emerge. Those stable axes snap back into existence, and you can see the arrow lock onto them. Those are the skeleton of the transformation. They are the axes the matrix is secretly built around. Why care? Eigenvectors are how we find the natural axes hidden inside data and inside systems. They tell us whether a system is stable or will blow up. They are the backbone of the next idea, principal component analysis. And in Google's original PageRank algorithm, The importance of every web page was literally the eigenvector of a giant matrix of links. Eigenvectors find the directions that matter. Let's see the most famous application right now, Principal Component Analysis, PCA, and its close cousin, the singular value decomposition, the SVD, are the most powerful application of eigenvectors you'll meet, and they solve a problem we all have: too much data, too many dimensions. Here's the idea. Look at this cloud of data points. The data clearly spreads more along one direction than another. PCA finds those directions of spread automatically. The red arrow points along the direction of greatest variation. That's the first principal component. The green arrow points along the next, and notice it's perpendicular to the first. These arrows are exactly the eigenvectors of the data's covariance matrix. The lengths are the variances, how much the data spreads along each. And here's the payoff. If almost all the spread is along the red arrow, then the green direction barely carries any information. So we can throw it away, describe each point by just its position along the red axis, and we've gone from 2 numbers down to 1 with almost no loss. That is dimensionality reduction, that's compression. Let me give you a concrete real-world example. Imagine you want to rank countries by development or happiness. You have dozens of indicators: income, life expectancy, education, freedom, social support, and so on. Dozens of dimensions impossible to eyeball. Run PCA and it finds that most of those indicators move together. Rich countries also tend to have longer lives and more education. So the first principal component bundles all of that correlated information into a single composite score. That one number, that's your happiness index, your development ranking, your human development index. PCA collapsed dozens of dimensions into the one axis that explains the most. The same technique compresses images, denoises data, and powers recommendation systems. It is eigenvectors earning their keep. Let's close out linear algebra with 3 words that sound abstract, but have a simple picture: span, rank, and independence. 2 vectors are linearly independent when neither one is just a stretched copy of the other, when they genuinely point in different directions. Watch. When these 2 arrows point different ways, together they can reach any point in the plane. The set of everything they can reach is called their span, and here the span is the whole plane. We say this set of vectors has rank 2, 2 genuinely independent directions, a full basis. Now watch what happens when I drag one arrow until it lies along the same line as the other. Suddenly they're dependent. One is just a multiple of the other. Their span collapses to a single line. They can no longer reach the whole plane. That's rank 1. The second vector adds nothing new. It's redundant. This is exactly how we measure whether data has redundant features, or whether a system of equations actually has enough independent information to be solved. Rank counts how many truly independent directions you have. Low rank means hidden redundancy. And redundancy, as PCA just showed us, is something we can compress away. That wraps up the data. Now, how does a model actually learn? Linear algebra gave us the data. Calculus gives us learning, because learning in machine learning is nothing more than gradually adjusting numbers to make a mistake smaller. And to know which way to adjust, you need to know which way is downhill. That direction, that slope, is what calculus provides. Every time a model improves, calculus is the compass telling it which way to step. Let's build that compass from the ground up, starting with the derivative. Everything in calculus starts here with one question. When I nudge the input of a function, how much does the output change? That ratio, change in output over change in input, is the derivative, and it's just a fancy word for slope. Let me make it concrete. Take any point on this curve. To measure the slope, I pick a second point a little distance away. That gap is called h, and I draw a line through the 2 points. That red line is called a secant, and its slope is the average rate of change between the 2 points, the rise over the run, the change in f divided by h. But the average over a gap isn't quite what we want. We want the slope at one exact point. So watch. I shrink the gap h smaller and smaller, sliding the second point toward the first. As h goes to 0, that red secant line rotates and settles onto the green line. The tangent. The tangent just kisses the curve at a single point, and its slope is the instantaneous rate of change. That is the derivative, written f prime of x. It's defined as a limit. The limit of that rise over run as the gap shrinks to nothing. Now slide x along the curve with me. Where the curve climbs steeply, the derivative is large and positive. Where it's flat, at a peak or a valley, the derivative is exactly 0. Where it falls, the derivative is negative. The sign and size of the slope tell you which way the function is heading and how fast. And that is the entire learning signal of machine learning. Picture the curve as the model's error. The derivative tells you which way is downhill, which way to nudge the model to make the error smaller. Take that step, measure the slope again, step again. That repeated process is gradient descent. And the backpropagation that trains every neural network is just the derivative, applied over and over, flowing the slope backward through the whole model. Master this one idea and you understand how machines learn. A derivative handles a curve in one variable, but a real model has millions of variables, so we need the multidimensional version, and it's called the gradient. The gradient is just a bundle of slopes, one partial derivative for each direction. The partial derivative along the x-axis asks, if I only move in x, how does the error change? The partial along y asks the same for y. Bundle them together into a vector, and that vector, the gradient, points in the direction of steepest descent straight uphill. Of course, we want to go down to make error smallest, so we step in the opposite direction, the negative gradient, downhill. These white arrows show that downhill direction at every point on the surface, and watch the yellow ball. Drop it anywhere and it simply follows the arrows down into the nearest valley. That rolling ball is gradient descent, the core algorithm that trains essentially every model in machine learning. Now watch the learning rate, the size of each step. With a small learning rate, the ball creeps down carefully and reliably. But watch when I crank it up. The ball takes huge steps, overshoots the bottom, and bounces back and forth, maybe even flying off entirely. Too small and training crawls, too large and it diverges. Finding that balance is one of the most important knobs in all of deep learning, and we'll come back to it. Here's the problem. A neural network isn't one function. It's hundreds of functions stacked, each one feeding the next. So how do we get the slope of the whole stack? The answer is the chain rule, and it is the engine of backpropagation. Picture a tiny pipeline. An input x flows into a function g, and g's output flows into another function f. Two stages nested. The chain rule says something wonderfully simple. The derivative of the whole pipeline is just the product of the local derivatives at each stage, the slope of f times the slope of g. You multiply the local slopes together. Watch the numbers as I move x. Each stage computes its own little slope, how sensitive its output is to its input, shown here in green, and the chain rule multiplies them together to get the red number, how sensitive the final output is to the original input. That's the gradient that backpropagation needs. And here's the beautiful part, the direction. The signal flows forward to make a prediction, but the gradient flows backward stage by stage, each step multiplying in one more local slope. That backward flow of multiplied derivatives is exactly what backpropagation does across a 100-layer network. Every layer asks the layer in front of it, how much did I contribute to the final error? And the chain rule passes the answer back. Forward to predict, backward to learn. That is how deep learning trains. Here's a small idea with big consequences. The Taylor series says you can rebuild any smooth curve using nothing but its derivatives at a single point. Start with just the value at a point. That's a flat line, a rough guess. Add the first derivative, the slope, and now you've got a tangent line that follows the curve for a short way. Add the second derivative, the curvature, and your approximation bends into a parabola that hugs the curve further. Watch as I add more terms. Each new derivative term makes a polynomial that clings to the true curve over a wider and wider range. Why does an ML engineer care? Because near a minimum, near the bottom of the error valley, the Taylor series tells us that any loss function looks like a simple parabola, and parabolas are easy to optimize. That single approximation, near the bottom, everything is a bowl, is the secret assumption behind many of the fastest optimization methods. It lets the optimizer pretend a horribly complicated loss is something simple, just where it counts. If the first derivative is slope, the second derivative is curvature, how the slope itself is changing, and in many dimensions, all those second derivatives bundle into a matrix called the Hessian. The Hessian tells you the shape of the landscape at a point, and its eigenvalues, remember those, classify exactly what kind of point you're standing on. Watch as I turn the curvature knobs. When both curvatures are positive, you get a bowl, a clean valley, a true minimum. This is the good case, gradient descent settles right in. Now I make one curvature negative and one positive, and you get a saddle. It curves up one way and down the other, like a mountain pass or a Pringle. Saddles are the villains of deep learning. They look flat, so the optimizer slows to a crawl, stuck, even though they're still a way down. And if both curvatures are negative, you're on a dome, a maximum. The worst place to be if you're trying to minimize. So the Hessian is the optimizer's map of the local terrain, bowl, saddle or dome. Knowing which one you're on tells you whether you've actually found a minimum or whether you're just stuck on a flat saddle that looks like one. The derivative measures slope. Integration is its opposite. It measures accumulated area, the total under a curve. Here's the simplest way to see it. To find the area under this curve, I slice the region into thin rectangles, measure each one, and add them up. That's called a Riemann sum. With just a few fat rectangles, it's a crude, blocky staircase. A rough estimate. But watch as I make the rectangles thinner and thinner. The staircase hugs the curve more and more closely, and in the limit, it converges to the exact area underneath. That limit is the integral. Why does this matter for machine learning? Because it's the very same machinery that turns a probability density into an expected value. When we want the average outcome of a random process, the mean of a distribution, we're integrating, summing up every possible value weighted by how likely it is. Area under a curve and the average of a random variable are the same calculation. That's the bridge into our final chapter. But first, optimization. So far we have the data in linear algebra and the learning signal in calculus. Optimization is where they come together into the actual training loop. Here's the whole idea in one sentence. Training a model means defining a number that measures how wrong it is, the loss, and then relentlessly adjusting the model's parameters to make that number as small as possible. An optimizer is the algorithm that decides how to take each step downhill. Get the optimizer right and a model trains in hours. Get it wrong and it never learns at all. Let's watch a few of them race. So what is an optimizer really? Picture our error landscape from before, hills and valleys. The optimizer is the strategy our ball uses to roll to the bottom. And there are several strategies, each smarter than the last. Let me line up 5 of them and start them from the same spot. The simplest is plain gradient descent, here SGD. It just follows the slope straight downhill. Watch it. On a long narrow valley, it zigzags, bouncing off the steep walls, making slow progress along the gentle floor. Functional but clumsy. Next, momentum. Just like a real ball gathering speed, it accumulates velocity, so it powers through flat regions and damps out the zigzag, faster, smoother. Then Adagrad and RMS prop. These are cleverer still. They give each direction its own step size, taking big steps where the ground is gentle and small steps where it's steep. And finally Adam, which blends momentum with those per direction adaptive step sizes. It's the best of both worlds, and it's why Adam is the default optimizer for almost all of deep learning, including the giant language models. When people train a model with billions of parameters, the optimizer turning the crank is almost always Adam or a close relative. Now let me show you why the learning rate matters so much. With a small learning rate, watch, every optimizer descends slowly but safely, all of them reaching the bottom. Now I reset and crank the learning rate up. See how the simpler methods overshoot, zigzag wildly, some even fly out of the valley and diverge, while the adaptive ones, especially Adam, stay far more stable, automatically taming their own steps. That robustness, working well across a wide range of settings without careful babysitting, is exactly why Adam won. It just works. The optimizer needs something to minimize, and that something is the loss function, the precise number that scores how wrong a prediction is. And different jobs need different scores. For predicting a continuous quantity, a price, a temperature, we use mean squared error. Take the gap between the prediction and the truth and square it. Watch the curve. It's a gentle parabola. Small mistakes barely matter. Big mistakes are punished by the square. It's smooth and forgiving. For classification, is this email spam or not? Is this a cat or a dog? We use cross entropy. And watch what happens here as the model becomes confidently wrong, predicting definitely spam when it's actually not. The loss doesn't just rise, it explodes toward infinity. Cross entropy punishes overconfidence brutally. It forces the model to be not just right, but appropriately humble about how sure it is. That sharp punishment for confident mistakes is exactly why cross entropy is the standard loss for training classifiers and language models, including how a language model is scored on predicting the next word. Here's a fact that explains a lot of the mystery and frustration of deep learning. The shape of the loss landscape decides whether training is easy or hard. A convex loss is a single, simple valley, one bottom, and no matter where you start, downhill always leads to the same global minimum. Watch, I drop 30 balls from random places, and every single one rolls to the same bottom. For a convex problem, gradient descent is guaranteed to find the best answer. Life is good. But most neural networks are non-convex, and now the landscape is bumpy, full of separate valleys, local minima, and saddle points. Watch what happens when I drop 30 balls here. They scatter into different valleys depending purely on where they happen to start. There's no guarantee any of them found the deepest one. This is why training a deep network can give different results on different runs, why the random starting point, the random seed, actually matters. We are wandering a complicated landscape, hoping to find a good enough valley, not necessarily the perfect one, and remarkably, in very high dimensions, good enough valleys turn out to be almost everywhere, which is the quiet reason deep learning works at all. We saw that the learning rate, the step size, is a delicate balance. Too big and you overshoot, too small and you crawl. So here's the clever trick the whole field uses. Don't keep it fixed. Change it as training goes on. That's a learning rate schedule. The strategy is intuitive. Early in training, you're far from the answer, so take big steps and explore boldly. Later, as you close in on the minimum, take small, careful steps so you settle gently into the bottom instead of bouncing around it. Big early, small late, watch the different shapes. Cosine decay glides the rate smoothly down, following a cosine curve, currently the most popular choice. Step decay holds the rate steady, then drops it suddenly at fixed milestones, and exponential decay shrinks it by a constant fraction every step. These schedules are absolutely critical for stable training of large models. Get the schedule right and a transformer trains smoothly. Get it wrong and the loss spikes and the whole run can fall apart. Here's the trap that catches every beginner, and the reason we split our data into two piles. It's called overfitting. When you train, you watch two numbers: the training loss, how well the model does on the data it's learning from, and the validation loss, how well it does on fresh data it has never seen. Watch the two curves. At first, both fall together. The model is genuinely learning useful patterns. But then they split. The training loss keeps dropping towards zero, while the validation loss bottoms out and starts climbing back up. That gap is overfitting. The model has stopped learning the pattern and started memorizing the training examples, like a student who memorizes the answer key instead of understanding the subject. It aces practice and fails the real exam. Two cures: early stopping, that dashed line, simply halts training at the moment validation loss is lowest, before the memorizing begins. And weight decay, watch as I increase it, gently penalizes large weights, which flattens that overfitting rise and keeps the model simpler and more general. The whole art here is building a model that generalizes to the real world, not one that just memorizes its homework. And generalizing to a world full of uncertainty is exactly what our final chapter is about. Here's the thing about the real world: it is uncertain. Data is noisy, measurements are imperfect, and the future is never guaranteed. A model that pretends to be certain is a model that's dangerous. So our final chapter is about embracing that uncertainty honestly, and the language for that is probability and statistics. Why do we need it? Because every prediction a model makes is really a statement about likelihood, not certainty. Probability lets a model say, I'm 70% sure, and statistics lets us check whether the patterns we found are real or just lucky noise. Let's build the toolkit starting with distributions. A probability distribution is simply a complete description of how likely every possible outcome is. The blue bars here are the true probabilities. The faint gray histogram is real samples drawn from that distribution, random draws piling up to match the shape. Let me show you the family. Bernoulli is the simplest. A single yes or no, a coin flip. Binomial counts the successes in many such flips. Poisson counts rare events in a window of time. How many emails arrive in an hour? Uniform makes every outcome equally likely. And the Gaussian, the bell curve, is the famous one we'll keep coming back to. Two numbers summarize any distribution, and you should know them both. The expectation or expected value, that's the green line, is the long run average, the center of mass, every outcome weighted by its probability summed up. And the variance, shown by the band, is how spread out the outcomes are around that center. Its square root is the standard deviation, the typical distance from the average. As I tweak these parameters, watch the center shift and the spread widen or tighten. Expectation tells you where, variance tells you how uncertain. Together, they're the vocabulary for talking about any random quantity. Now I want to show you what might be the most surprising and important result in all of statistics. The central limit theorem. It explains why the bell curve is everywhere. Here's the setup. Take any source of randomness, and I mean any. Watch, I'll pick a deliberately lumpy, ugly, non-normal source. Nothing bell-shaped about it. Now, instead of looking at single values, I take a handful of samples, average them, and record that average. Then I do it again and again, thousands of times, and I look at the distribution of all those averages. Watch what happens as I increase the number of samples in each average. The distribution of the averages becomes a smooth, symmetric bell curve, a Gaussian, no matter how weird and lumpy the original source was. The messiness washes out. That is the central limit theorem, and it is almost magical, and it explains something profound about nature. Why is the bell curve everywhere, in human heights, in measurement errors, in test scores, in noise of every kind? Because almost everything in the world is the sum of many small, independent influences. Your height is the combined effect of thousands of genes and environmental factors added together. And whenever many small random things add up, the central limit theorem guarantees the result is a bell curve. That's why the Gaussian appears in virtually every dataset you'll ever touch, and why so much of machine learning quietly assumes it. Often, we don't have just one variable, we have two, and we want to know, do they move together? That's covariance and correlation. Covariance asks a simple question: when one variable is above its average, does the other tend to be above its average too? Watch the cloud as I slide the target. When I set a strong positive relationship, the points line up along a rising diagonal. When one goes up, the other goes up. When I dial it to 0, the cloud becomes a shapeless blob. The two variables are unrelated. And when I make it negative, the cloud tilts the other way. When one rises, the other falls. Covariance captures that, but its raw number depends on the units. So we rescale it into correlation. A clean number between -1 and +1. +1 is a perfect rise together, 0 is no relationship, -1 is a perfect opposite. And here's the lovely connection back to where we've been. The matrix of all these covariances is exactly the matrix that PCA decomposes to find a dataset's principal directions. Covariance is the bridge between statistics and the linear algebra we started with. This is one of the most important and most counterintuitive ideas in all of statistics. Bayes' theorem. It's how we update a belief when new evidence arrives, and getting it wrong has cost people dearly, including doctors. So let's walk through it carefully. Bayes' theorem says the probability you're sick given a positive test equals the probability of a positive test given you're sick times how common the disease is to begin with, divided by how common positive tests are overall. The key character in that sentence is how common the disease is to begin with, the prior. Let me make it concrete with this grid of 10,000 people. Suppose a disease is rare. It affects 1% of people. So, out of 10,000, just 100 are truly sick, the red squares. Now we have a good test. Its sensitivity is 99%, meaning if you are sick, it catches you 99 times out of 100. And its specificity is 95%, meaning if you are healthy, it correctly says so 95% of the time. Now, here's the surprise. You take the test and it comes back positive. How worried should you be? Most doctors say 99%. Let's count. Of the 100 truly sick people, the test catches 99. But of the 9,900 healthy people, 5% get a false positive. And 5% of 9,900 is nearly 500 people. So the positives are 99 real plus almost 500 false alarms. Out of everyone who tested positive, the fraction who are actually sick is 99 divided by about 600. Only around 16%. Let that sink in. A 99% accurate test and a positive result still means you're probably fine. Only a 1 in 6 chance of being sick. Why? Because the disease is so rare that the prior dominates. The false alarms from the huge healthy population swamp the true positives. Watch what happens when I raise the prior, making the disease more common. Now, a positive result means much more. The evidence is the same. The conclusion changes completely based on the prior. This is Bayesian thinking, and it's everywhere in machine learning, spam filters, medical AI, every system that combines prior knowledge with new evidence. Never trust a test result without asking how rare the thing it's testing for actually is. Often we know the shape of a distribution, but we need actual samples from it, concrete values to work with. Sampling is how we get them, and the simplest recipe is wonderfully intuitive. It's called rejection sampling. Watch. I want samples shaped like this curve, so I just scatter darts completely at random inside the box. Then I apply one rule: keep every dart that lands under the curve, the green ones, and throw away every dart above it. That's it. The survivors, the ones that fell under the curve, automatically follow the target distribution with no fancy maths at all. Where the curve is tall, more darts survive. Where it's low, fewer do, so the kept points naturally pile up to match the shape. It's a little wasteful, we throw away a lot of darts, but it's the fundamental building block behind the powerful sampling methods like Markov chain Monte Carlo that let us work with distributions far too complicated to handle with formulas. Whenever a generative model produces a sample, an image, a sentence, some descendant of this idea is at work. Let's finish the toolkit with the workhorse of every data-driven company, the A/B test. It's how you decide with real statistical rigor whether a change actually worked or whether you just got lucky. The setup: you show version A to one group and version B to another, and you measure, say, how many people clicked. Now you can't just declare the higher number the winner because of random chance. So we do two things. First, around each rate we draw a confidence interval, those error bars, a range that says, given our sample, the true rate is very probably somewhere in here. The fewer users, the wider and more uncertain the bars. Second, we compute a p-value. The p-value answers one precise question. If there were truly no difference between A and B, that's the null hypothesis. What's the probability we'd see a gap this large just by chance? If that probability is tiny, conventionally below 5%, then pure luck becomes an implausible explanation, and we declare the result statistically significant. Watch. When I set A and B nearly equal, the p-value is large, and the test says, no real difference, keep looking. When I make B clearly better, or pour in more users, the p-value collapses and the verdict flips to significant. This is hypothesis testing, and it's how we keep ourselves honest. It's the discipline that separates a real, repeatable improvement from a random fluctuation we got excited about. And in machine learning, it's how we decide whether a new model is genuinely better than the old one, or just luckier on this particular test set. And that's the whole picture. 4 areas of mathematics: linear algebra for the data, calculus for the learning signal, optimization for the training loop, and probability for the uncertainty. None of it is magic. It's vectors and slopes and bell curves, each one a simple idea you can see. And together, they're enough to understand how every modern machine learning model actually works. Here's the best part: this entire deck, every single simulation you just watched, is open and interactive, and you can run it yourself. It's built in Doodle Code Studio. Head to the GitHub repo on the screen, install it locally, and open the example file. It's the one called ML Simplified, sitting right inside the examples folder. Tweak every knob, drag every arrow, and build the intuition with your own hands. That's when it really clicks. If this helped the maths feel a little less like magic, I'd love to stay connected. You'll find me on LinkedIn, that's Carter-XAI, where I share more of this kind of thing. And please follow me on YouTube and subscribe to the channel. That's at Carter_Mohideen, so you don't miss what's coming next. Thank you so much for watching, take care, and I'll see you in the next one.